We're now on our last topic, or our last section of the course, namely about cardinality. And I want to talk to you in this video about the cardinality of finite sets. So let's see how we're doing here. So let's talk about finite sets, and something about pigeons come in here, or at least pigeonholes. So let's talk about the size of a finite set. So we define the cardinality of A, written by putting these absolute value signs around A, to be the number of elements in A. Now, when we count the number of elements in A, we typically actually, in our minds, count off the numbers 1, 2, 3, 4, 5, 6. So for example, if a set here, and so I have a set here of place names, and numbers 1, 2, 3, 4, 5, 6, when we count off the elements of this set, we're basically saying, hey, there's 1, there's 2, there's 3, there's 4, 5, 6. And so what we're really doing when we count the elements of a set, when we count them in our head or out loud, is we're building a function from the set to the a subset of the natural numbers, namely starting at 1, going to n, in this case 6. And this function that we're building is both injective, because different objects map to different numbers when I count them out, and it's surjective because each number here is mapped to by an object over here. So this function that we're busy building when we're counting out the objects in a set is actually a bijection. And we can use this idea to define what we mean by two sets having the same size. So, and the benefit of this definition in terms of functions is we can extend that definition later on to a definition that works not just for finite sets, but for infinite sets, which is really the main thing that we want to get to here in this last part of the course. So let's take two sets A and B. We say they have the same cardinality if either, well, they're both the empty set. It's kind of a boring case, but we have to take it into account. Or, more interestingly, if there's a bijection between A and B. And in this case, we write that the cardinality of A is equal to the cardinality of B, and we say that the sets are equinumerous. Now notice here, when we've defined this notion of equinumerous and cardinality, we haven't actually introduced any integers at all. So we're writing this, but this statement depends on the existence of a bijection, not that this is equal to 6 and that this is equal to 6. So we're sort of escaping from the idea that the cardinality has to be a number, and we're expressing the cardinality in terms of the existence of a bijection, the existence of a function. Now, when A and B are not equinumerous, when they have different sizes, well, then there's no bijection between them, and we write this. We just put a slash through the equal sign. Okay. Now, when we think about this a little bit, special case, if A is the empty set, we write that the cardinality of A is equal to 0, and we do this because there's no way to define a bijection between empty sets. Okay, we define functions on non-empty sets. Okay, so again, this is a special case that we sort of have to put to one side. Now, when the set is finite, then we often write that the size of A is some natural number n, and this we take to mean that there's a bijection, just like there was on the previous slide, between A and the subset of the natural numbers 1 through n. And then, if we have two sets both having n being some finite natural number n in natural numbers, if they both have the same size being this finite number n, then we really have a bijection from A to n and a bijection from B to 1, 2, 3, 4, 5, 6, 7, 8 up to n, and B to that same set. And so if we form the inverse function here and compose it with this, then we really have a bijection between these two sets. And so we're using the property that a bijective function has an inverse, and that the composition of bijections is bijection. Now, as I said, this definition avoiding, except here in this finite case, avoiding defining the cardinality in terms of an integer, but instead in terms of functions, allows us to extend this definition up to infinite sets and talk about that in some sensible way. Now, if we have finite sets that are not equinumerous, so for example, here's a set of 5 things and a set of 3 things, then, well, if we start to think about trying to construct functions between these sets, well, because there's 5 things here and 3 things here, it's pretty easy to see that we can't build a bijection between them. Now, it is easy to build a surjection. We can just wire up things like this so that everything here is hit by something, just like this. So it's easy to build a surjection, just like that, but not so easy to build an injection. So if we try this again, you see I can put that there and that there and that there, but it doesn't matter how I join up those first 3 elements, by the time I get to these two remaining elements here in A and I need to connect them to something, I need to say what their output is under this function, well, it doesn't matter what we do, we're going to have two things mapping to the same thing. So this fails to be injective. Now, to formalize this reasoning that I used here, we can use something called the pigeonhole principle. So this is the pigeon that came up earlier in my video. So what is the pigeonhole principle? This is due to Dirichlet, and the pigeonhole here refers to an old-fashioned mail room where you put letters into little boxes, and those boxes are called pigeonholes. So this doesn't say anything very deep, but it helps to formalize the idea here. So we've got n objects being placed in k boxes. The idea is what happens if n is smaller than k, that is we have fewer objects than boxes, or if we have more objects than boxes. What can we say? Well, if we have fewer objects than boxes, then at least one of the boxes, doesn't matter how we put the objects in things, at least one box has 0 elements in it. So one of the boxes is completely empty. On the other hand, if we have more objects than boxes, well then at least one box has at least 2 objects in it. Doesn't matter how we arrange things, one of the boxes has to have 2 things or more in it. Now this last case we can refine a little bit more to say, well, if n is bigger than k, then at least one box has the ceiling of n over k objects in it. Okay, now, it could be more than one box, but at least one box has to have this many objects, or at least that many objects in it. And the proof of this theorem is pretty straightforward, just using the contrapositive of each statement. So if we look at this one, if we assume each box contains at least one object, so the contrapositive of this statement, then the total number of objects is the opposite inequality. And similarly for the second case, if we assume each box has at most one object in it, then the total number of objects is n, which is less than or equal to k. Okay, so proving the contrapositive of these statements is really quite straightforward. Now the pigeonhole principle turns out to be very, very useful, not just for what I'm about to do now, but much, much more generally. So if we take two finite sets and let f be a function from a to b, well, if the size of a is bigger than the size of b, again, remember we're talking about finite sets here, then this function can't possibly be an injection. On the other hand, if the size of a is less than the size of b, then the function can't possibly be a surjection. And again, these are quite easy to prove by the pigeonhole principle. So indeed, if we prove the first one here, if we assume that a is bigger than b, then by the pigeonhole principle, when we take the images of things in a and put them onto the things in b, then at least one element in b is the image of two things in a. So there are two things in a that are different that map to the same thing. So this a1, a2 here, a1 is not a2, that map to the same thing. And so f is not injective. And you can prove the surjectiveness in a similar way. If a is smaller than b, then by the pigeonhole principle, when I take things here from a and put them in b, at least one of the elements of b is not the image of anything in a. And so there's some b in b so that no a maps to it. And so f is not surjective. Okay, now these statements are often, well, as we see, they're not so hard to prove, but actually it's the contrapositive of these statements that may be more useful, namely, and again, remember this is finite sets. If we can build an injection from a to b, then a has to be smaller than or the same size as b. On the other hand, if we can build a surjection, then a has to be bigger than or equal to b. And remember, this is just for finite sets, and when we extend that idea to infinite sets, well, we'll get to that later in a later video. So now, here's an example of what else we can do with the pigeonhole principle other than just this little statement about functions. So here's a result, namely there are 2 powers of 3 whose difference is exactly divisible by 220. And the proof isn't so hard. It just relies on the fact that the pigeonhole principle tells us that a certain structure must exist. You know, you have a certain number of boxes and you start putting things in boxes. At some point, 2 things have to go in the same box. Okay? So if we consider just the first few numbers in this sequence, so we just 0, 3 to the 1, oh, that's not 0, that should be 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3, and so forth, up to 3 to the 220. So we've got 221 numbers here. And then think about their remainders when we divide them by 220. Well, we've got 221 things, so we get 221 remainders when we compute all of them, but there are only, when I divide by 220, there are only 220 boxes. So we've got 220 possible remainders, but 221 numbers. So when we compute all of those remainders, two of those boxes must have the same, must have two things in it. So that is, there must be two numbers, 3 to the I, 3 to the j, that have, when I divide by 220, have the same remainder. Because I have 221 numbers that I'm going to divide by 220 and look at their remainder, but there can only be, at most, 220 remainders when I divide by 220. So one of those boxes has two things in it. And so then if I look at the difference between these two numbers, 3 to the I, 3 to the j, well, those remainders will cancel each other, and I'll have left just a multiple of 220. And indeed, if you do this on a computer quickly, you can check that, checking remainders 220, you can quickly find that 220 divides 3 to the 20 minus 3 to the 0. Okay, so you can check that pretty quickly. Okay? But again, by thinking about how many boxes things can go in, we can see that two of these numbers, when I compute the remainders, end up in the same box, and that's enough to give us the result. Here's another similar sort of pigeonhole principle example. If we take 5 points and place them in an equilateral triangle of side length 1, there's a pair of points, no matter how I put things down, where the distance between those points is no bigger than a half. And the proof is quite slick. Namely, if we take that unit triangle and split it up into 4 subtriangles like this, so here's my unit equilateral triangle, and I split it up into 4 subtriangles like this, the side length here of each of these little subtriangles is a half, and there are 4 of them. So if I put points down, doesn't matter how I put the points down, one of these triangles has to include 2 points, because I've got 5 points and 4 triangles. So one of these triangles must contain 2 points, and the points inside that little triangle can't be further away than a half. So the 2 points inside that triangle have to exist, just because there are 5 and 4 triangles, and the 2 points can't be separated by more than a half. And that gives us the result. Now there's one more thing I want to prove here, and this is maybe not so rigorous, but this is an observation that if you have lots and lots of data, that you can get some very, very spurious correlations. This kind of comes to us from the pigeonhole principle. So think about, at least initially, how many function shapes you can draw. So think about a function of time and how it can vary during that time. So, you can think about functions that do something like this, or something like that, or something like that, and so forth. So think about how many different shapes you can draw, and then think about how many time series data exist in the world. So things like, dairy production in Quebec over the last century, or iron ore mined in Alberta, for example. Things like that. Just how much of something exists over a given period of time. Well, by the pigeonhole principle, because there really aren't that many shapes you can draw, but there's a huge number of data sets, by the pigeonhole principle, each shape that you can draw will be fitted by many, many different data sets, because there's way more data sets than shapes. And so that means you can put, just by the pigeonhole principle, a given shape will have lots of different data sets that fit it. And these data sets, because of that, appear really correlated. And so here's an example of this effect. Namely, I have some data here which shows the number of maths PhDs awarded since 1996 versus the total amount of uranium stored at US nuclear power plants. And you can see that these actually match up quite well. And so if you compute the correlation between these two quantities, that correlation is actually really high, even though I sincerely hope there's absolutely no correlation, no causation that links these two things. And so this is a really weird example of something that sort of comes to us from the pigeonhole principle, or something like the pigeonhole principle. Namely, if you've got a number of boxes and a number of objects, if you have lots and lots of objects, way more than the number of boxes, then those boxes are forced to contain several objects. And this is one way that this manifests. And this is a really weird and very interesting little phenomenon here, that if you have lots of data, you get lots of correlations, many of them making no sense at all. And I invite you to go and search engine your way to the book Spurious Correlations, book and website by Tyler Vegan. It's a very interesting little idea. And that's where I'm going to stop this video.